Bristol Community College, Mathematics with Dan Avedikian, Math 131, Elements of College Mathematics, Section 3.3, Problem 4. This is Section 3.3, Problem 4. It says the Fall River Furniture Company can make desks and chairs. The desks and chairs each require milling, which is cutting, routing, and shaping. They require assembly and finishing. The finishing consists of sanding, staining, and polyurethane. Each week, the company has 70 hours of milling time, 40 hours of assembling time, and 90 hours of finishing time. Each desk requires 2 hours of mill work, 1 hour of assembly, and 1 hour of finishing. Each chair requires 1 hour of mill work, 1 hour of assembly, and 3 hours of finishing. If the profit is $110 per desk and $80 per chair, how many of each should be made each week in order to maximize the profit? So just to set up the problem, we have a 4-part process. Part 1 is identify the variables. Part 2 is write out the object function. Part 3, set up the constraints. And Part 4 include that each variable is greater than or equal to 0. And then we have to solve it, which is 4 more parts. So just to set it up, first identify the variables. The variables are the two things being made. And in this case, they're making desks and chairs. The desks get mentioned first, so I'm going to make that x. So x equals desks. And the chairs are mentioned second, so y equals chairs. So that's step 1, identify the variables. We identify them. Step 2, write out the object function. And the instructions for that are look for information. It's typically about profit and usually near the end of the problem. And this problem is a pretty standard problem. Near the end, they do mention profit. It's $110 per desk, and again, those are x, and $80 per chair, which is y. So for the object function, we want to maximize z equals 110x, because 110 is the profit per desk and x is desks, and then plus 80y, because 80 is the profit for chairs and chairs are y. So this is step 2, maximize z equals 110x plus 80y. Step 3, set up the constraints. That's where most of the work is. So we're going to do subject to. And now what's going to limit the number of desks and chairs that can be made is the number of hours available for each of the operations, milling, assembly, and finishing. So there are 70 hours of milling time available. So let me put a 70 here, and I'll just write next to it mill. Next, 40 hours of assembly. I'll abbreviate a little bit for assemble. And 90 hours of finishing time. So now what we have to do is for each constraint, say how much each desk takes up and each chair takes up. So if we look back to the original problem, I find the sentence that says each desk requires 2 hours of mill work, 1 hour of assembly, and 1 hour of finishing. Now desks, again, are x. So for the mill work, it's 2 hours each, so 2x, 1 hour of assembly, so 1x, and 1 hour of finishing, so 1x there also. So again, desks are x, and each desk takes 2 hours of mill work, 1 hour of assembly, and 1 hour of finish. Now next are the chairs, they're y. So I look again back to the original problem, and I find the sentence about the chairs. It says each chair requires 1 hour of mill work, 1 hour of assembly, and 3 hours of finishing. So for the y, so for mill work, it's 1 hour per chair. For assembly, 1 hour per chair, so 1y. 3 hours of finishing for the chairs, so 3y. So again, chairs are y, 1 hour for each chair for mill work, 1 hour for each chair for assembly, and 3 hours for each chair for finishing. Now, I'll put a plus between the x and y values that I have in each constraint. And the inequality symbol for each one is a less than or equal to, because like before, say we have 70 hours of millwork available, you can use all 70 or a little less, say 65. You can't use 72 hours of millwork because there just are not 72 hours available. It has to be 70 or a little less. Same with the assembly and the finishing, why you have to have less than or equal to. This is step 3 of our 4-step process. Step 4 is for each of the products that you're making, it has to be mentioned that they are greater than or equal to 0. You cannot make a negative number of desks. You cannot make a negative number of chairs. So that's how we set the problem up. Now we have to solve it. So to solve a problem like this one, what we're going to do is graph our feasible region, label our corner points, fill in our chart, and then state our solution. Now, the millwork constraint, let me see how many colors I have. I can do millwork in purple. So I'll make one line purple. So my XY chart, I'm going to pretend that my millwork constraint is actually 2x plus 1y equals 70 instead of less than or equal to. So I want to find 2 points with x and y values that would make that true. So first, if I zero the x, I just have y equals 70. And then if I zero the y, the 1y in my equation would drop out, and I have 2x equals 70. So 2 times 35 would make 70 equals 70. So one line is going to be drawn in purple. I'll do the next one in red, the assembly constraint. So I'll make my little XY chart next to my assembly constraint. Again, I want to pretend instead of x plus y is less than or equal to 70, I want to pretend it's x plus y equals 70. So this one's fairly easy. If I zero out the x, I have y equals 40. And if I zero the y, I would have x equals 40. And now the finishing constraint I will do in green. So x, y. So now I want to pretend it's 1x plus 3y equals 90, not less than or equal to 90, equals 90. And find 2 points with x and y values that would make that equation true. So first, if I zero the x, I would be left with 3y equals 90. So y would have to be 30. And then if I zero the y, I'd have x equals 90. Now, based on the numbers I have here that I'm going to need to graph, my biggest y value is a 70, my biggest x value is a 90. I definitely don't want to go one at a time. Going by tens to set up my graph for my feasible region is probably the most sensible choice. Again, you can go with whatever you want as long as you label it. I like tens, and I'll do them both by tens. They don't both have to be labeled in the same interval, but it works good for this problem. So the y's can go 10, 20, 30, 40, 50, 60, 70. That's actually enough, but I might as well take it to 100, 80, 90, 100. That's so easy to do. And then for the x's, again, I'll run them by tens out to at least 90, but I'll set it to 100 also. So the x's will go 10, 20, 30, 40, 50, 60, 70, 80, 90. So that's really as far as I have to go to accommodate my biggest x, but I can put one more in so easily, 100. So now let me start drawing these constraints graphically. So the first constraint that I have to draw, 2x plus 1y is less than or equal to 70, I have to put the point 0, 70 on my graph and represent it with a purple dot because I started doing that with purple. So over 0 up 70, we'll get a purple dot. Over 35 up 0, we'll also get a purple dot. I do not have 35 exactly on my number scale, so by eye, I'll estimate as best I can where over 35 up 0 should be, and I'll put a purple dot. And I will connect my 2 purple dots with a purple line. And now I will have to determine if I want to shade above my purple line or below it. Again, what I need to do is find my test point that I like to use, make sure it's not on the line, and it's not. 0, 0 is not on the line. 0 for x, 0 for y in my millwork constraint. will give me the result 0 is smaller than 70, which is certainly true. So my test point came from underneath the line. It's giving me a true result. So the test point is in the shaded region. The underneath portion is shaded. Now, the next constraint down, 1x plus 1y is less than or equal to 40, was the assembly constraint. I started listing the parts of that in red. So let me put that on the graph in red. I'm going to put one red dot at over 0 up 40. And then I'll have a second red dot at over 40 up 0. And I will connect my two red dots with a red line. And I need to decide if I should shade below the red line or above the red line. So as usual, I use 0, 0 as a test point to see if I get a true or false result for that constraint that I'm graphing. So the one for assembly where 1x plus 1y is less than or equal to 40. I put in a 0 for x, 0 for y. The result I get is 0 is less than 40. True statement. So again, my test point's beneath the line. It gives me a true result, so the test point's in the shaded portion of my graph. So I'll shade beneath the red line. And now I have yet another constraint for finishing that I did in green. It's 1x plus 3y is less than or equal to 90 for the finishing constraint. So to continue in green, I'm going to have to put a green dot on my graph over 0 up 30. And a second green dot on the graph at over 90 up 0. And I will connect those two green dots with a green line. And I'll need to determine whether I should shade below the line or above it. It also winds up being below. Same type of reasoning. I'm going to use a test point that I like to use, 0, 0. And I get to use it because it's not on the line. If it was on the line, I'd have to pick something else. So to take my constraint of 1x plus 3y is less than or equal to 90, put in the x and y coordinates of my test point, which is 0 for x, 0 for y. And I would get 0 is smaller than 90. And is that true or false? It's certainly true. So the test point must be in the shaded region because you got a true result when you put it in the thing that you're graphing. So that means in this particular case, the green line gets shaded underneath. And I won't even shade too far. So the area that satisfies all of my constraints simultaneously is the feasible region. I should include, as usual, the x greater than or equal to 0 means that I can only use points with a positive x value. Y greater than or equal to 0, I can only use points with a positive y value. So now, the area that satisfies all of the constraints simultaneously is the feasible region, which I will shade in heavily. I'm careful not to shade in too much. There are some areas that are very close to the feasible region that are not included in the feasible region. So that's the first part of a 4-part process, graph your feasible region. Next, I have to label the corner points. So as I do that, I have one corner point over 0 up 30. That's the corner point of my feasible region, which again is a bounded feasible region. I have a corner point at 0, 0. That cannot be the maximum, but it is a corner point. I have a corner point. This purple line comes down and makes the boundary of my feasible region. So as I look back to the work that I did for the purple line, my corner point is over 35 up 0. And now I have two corner points that are not on the x-axis or y-axis. They're out in the middle, which means I'm going to have to solve some equations simultaneously. I'll see if I can fit them up in this corner here So I'll leave myself room for some other work. So one of the points that I have is the point where the green line and red line intersect with each other. So the green line was the finishing constraint, the red line was the assembly constraint. So let me start by writing those constraints as equations. So I'll have one of them that is 1x plus 1y is equal to 40. That's the red line that's coming in for a point of intersection. And the green line is 1x plus 3y equals 90. Now, I can either go positive x or negative x and cancel the x's, which is the easiest way, or I could do negative 3y, positive 3y. That would work also, but the x's are easier, so I'm going to leave the bottom equation unchanged. 1x plus 3y equals 90. And the top one, I have a 1x. I want to make it a negative 1x for my top constraint, so I'm going to do everything times negative 1. So 1x times negative 1 is negative 1x. Then 1y times negative 1 is minus 1y. Then I have equals, and then 40 times negative 1 is negative 40. And now when I combine the two equations that I have, negative 1x and positive 1x cancel. Negative 1y, positive 3y is positive 2y. Negative 40 and positive 90 is 50. So if 2y equals 50, if you divide out the 2, you'll have y is 25. So the point where the red line and the green line intersect has a y coordinate of 25. Now, the x coordinate can be found by taking my y equals 25, go back to either of the original equations, and find the x coordinate. Well, the top equation, if I know y is 25, and I'm adding an x to it to get 40, the x has to be 15. So the x coordinate, let me just make a spot for it, is 15. Now, I have another point of intersection down here that's one of my corner points. And it's where the purple line for the milling constraint intersects with the red line for the assembly constraint. So let me solve those simultaneously. So the purple line for the milling constraint is one of those lines that intersect. So I'm going to start off with 2x plus 1y equals 70. Again, I treat it as an equation. And the red line, which is the assembly constraint, is going to be 1x plus 1y equals 40. Now again, I could cancel the x's, 2x and negative 2x. I could cancel the y's, positive 1y, negative 1y. Y's would be easier. Either one would work, but y's would be easier. So what I'm going to do, I'm going to leave the top equation unchanged. It will say 2x plus 1y equals 70. The bottom equation, I'm going to multiply everything times negative 1. So 1x times negative 1 is negative 1x. 1y times negative 1 is negative 1y. And 40 times negative 1 is negative 40. Now I've made two new equations which I want to combine. And when I do, 2x and negative 1x will be x. Positive 1y, negative 1y just cancel. And then positive 70, negative 40 is 30. So the corner point of my feasible region that I'm working on currently has an x coordinate of 30. Now to find the y coordinate, take your x value of 30, go back to either of the original equations we started working with and put it in. So one of the original equations is 1x plus 1y equals 40. So if I put in 30 for x, 30 plus some value for y has to add up to 40. Well, the y must be 10. And again, as you look at the graph, over 30 up 10, it seems reasonable. And the other one that we did before, that we got 15, 25 for the coordinates of the corner point, seems reasonable based on my graph. So what happens now is I have to set up the chart and plug each corner point into the object function and see what type of output I get. And I'll do that in a different color, just so I don't mix the colors together too much. I'll try and keep it clear which step I'm on. So this is step 3 of a 4-step process of how you find the answer, and I'm filling this chart out. The first column is for corner points. The middle column, I give myself a little extra room, is for the object function. So for the particular problem I'm working on right now, the object function is z equals 110x plus 80y. And the last column is for output. I have 5 corner points, so I'm going to need to have 5 rows in the chart I'm making. And I'll list the corner points. I have a corner point at 0 for x, 30 for y. I have another corner point, 15 for x, 25 for y. I have another corner point at 30 for x, 10 for y. I have another corner point at 35 for x, 0 for y. And the last corner point, 0x and 0 for y. So I'll plug the x and y coordinates of each corner point into the x and y values of my object function and find the output. So the first corner point, 0, 30, means the 110x becomes 110 times 0 plus 80y is 80 times 30. 110 times 0 is 0. 80 times 30 is 2400. 0 plus 2400 is 2400. So that means that we can find the profit of $2,400 by making 0 desks and 30 chairs. Now the next one down, 1525, means what profit do we get by making 15 desks and 25 chairs? So the 110x becomes 110 times 15, and the 80y is 80 times 25. So 110 times 15 is 1650. 1,650. Let me double check that to make sure. Yes. And then 80 times 25 should be 2,000, but since the calculator is in my hand, I'll check that too. It's 2,000. So now 1,650 plus 2,000 is 3,650. So that's more profit, which is better. So that means that you can get a profit of $3,650 by making 15 desks and 25 chairs. So now the next corner point, 30, 10, 30 for x, 10 for y, means what happens if you make 30 desks and 10 chairs. So 110 times x becomes 110 times 30, and then 80 times y becomes 80 times 10. So 110 times 30 is 3,300, right? 3,300. And 80 times 10 is 800. So 3,300 plus another 800 is 4,100. That's even better. So you can make a profit of $4,100 by making 30 desks and 10 chairs. So the next corner point is 35, 0. 35 for x, 0 for y means what happens when I make 35 desks and 0 chairs. So 110 times x is 110 times 35, plus 80 times y is 80 times 0. So 110 times 35, I think, is 3,850, but I should check that. 3,850. And then 80 times 0, of course, is 0. That's very easy. So 3,850 plus 0 is 3,850. So we can make a profit of $3,850 by making only desks until we run out of material, basically, is what it means. 35 desks and no chairs. The 0, 0 last corner point is going to be 0, of course. 110 times x becomes 110 times 0. 80 times y is 80 times 0, which is 0 plus 0, giving us a profit of 0 by not making any desks and chairs, which, of course, is the point. Now, we want the most profit, not the least. So our options for how much profit is possible with the different combinations of desks and chairs are a profit of $2,400, $3,650, $4,100, $3,850, or $0. Well, the most profit is $4,100. So the final solution, I can put maximum profit of $4,100 by making, let's see, so that came from making 30 desks and 10 chairs. So I have a maximum profit of $4,100 by making 30 desks and 10 chairs.